Hi, welcome to non-destructive testing subject. Today topic is visual inspection method. Myself, G. Sundar Raju, Assistant Professor, Mechanical Engineering, Banari Amman Institute of Technology, Tamil Nadu. Visual inspection is a common method of quality control, data acquisition, and data analysis. Visual inspection, used in maintenance of facilities, mean inspection of equipment and structures using either or all of raw human senses such as vision, hearing, touch, and smell or any non-specialized inspection equipment.
In this media, you will learn about visual inspection of welds, its advantages and disadvantages. Visual inspection is performed to know whether the weld penetration and contour are satisfactory. The weld surface and joints are examined with the help of a magnifying lens. Today's optical systems may include special probes, spectrometers, real-time imaging, and analysis using notebook computers. Visual inspection is carried out in 3 stages, namely, visual inspection before welding, visual inspection during welding, and visual inspection after welding. In visual inspection before welding, the following factors should be ensured. Weldable quality of the material to be welded. Properly prepared edges of the workpieces for welding. Proper cleaning of the base metal. Setting of proper root gap. Current setting, according to the size of the electrode and position of welding. Need for any jigs and fixtures to ensure proper alignment. During welding, the following visual inspections are made. Studying the sequence of weld deposit. Examining whether each weld is done satisfactorily before making the next run in multi-run welding. Checking the shape of the bead, angle of electrode, control of spatters, amperage, speed of travel, and arc length. Checking the manipulation of electrode, blowpipe, and filler material. Observing keenly the molten pool for proper fusion. Visual inspection needs to be done after welding to identify if there are any of the following flaws. Improper shape or profile of the weld. Surface defects of the weld. Undercuts and overlaps. Excessive convexity of contour. Improper run and penetration of the weld. Distortion of the workpieces. Unfilled cavity. Main advantage of visual inspection is that it is the simplest, fastest, and economical method. Main disadvantage of visual inspection is that internal defects cannot be determined. Thus, you have learned about visual inspection of welds, its advantages and disadvantages.
Why are metal tested? Today modern manufacturing, fabrication, and in-service inspections to ensure product integrity and reliability. To prevent failure in use. To select the specific material for specific applications. NDT used to control manufacturing processes, lower production costs and to maintain a uniform quality level. During construction, NDT is used to ensure the quality of materials and joining processes during the fabrication and erection phases, and in-service NDT inspections are used to ensure that the products in use continue to have the integrity necessary to ensure their usefulness and the safety of the public. Visual inspection is a common method of quality control, data acquisition, and data analysis. Visual inspection, used in maintenance of facilities, mean inspection of equipment and structures using either or all of raw human senses such as vision, hearing, touch. The 6 most frequently used test methods are MT, PT, RT, UT, ET, and VT. Each of these test methods will be described here, followed by the other, less often used test methods. 1. Visual testing, VT. 2. Liquid penetrant testing, PT. 3. Magnetic particle testing, MT. 4. Ultrasonic testing, UT. 5. Radiographic testing, RT, and 6. Electromagnetic testing, ET. Visual testing is the most commonly used test method in industry. Because most test methods require that the operator look at the surface of the part being inspected, visual inspection is inherent in most of the other test methods. As the name implies, VT involves the visual observation of the surface of a test object to evaluate the presence of surface discontinuities. This technique is developed by Electric Power Research Institute, EPRI, in the early 1980s. It is used in castings, forgings, and welding components. Visual inspection is normally the first step in the examination process. Generally, almost any specimen can be visually examined to determine the accuracy of its fabrication. For example, visual inspection can be used to determine whether the part was fabricated to the correct size, whether the part is complete, or whether all of the parts have been appropriately incorporated into the device. Primary method of NDT. A simple visual test reveals gross surface defects. Physical principle: illumination of the test specimen with light. Equipments used are very simple and portable. Most valuable NDT tool: human eye. Mainly performed to obtain the general condition of components. While direct visual inspection is the most common non-destructive examination technique, many other NDE methods require visual intervention to interpret images obtained while carrying out the examination. For instance, penetrant inspection using visible red or fluorescent dye relies on the inspector's ability to visually identify surface indications. While direct visual inspection is the most common non-destructive examination technique, many other NDE methods require visual intervention to interpret images obtained while carrying out the examination. The basic principle of visual inspection is: the eye can perform accurate inspections to detect size, shape, color, depth, brightness, contrast, and texture. Visual testing is essentially used to detect any visible discontinuities, and in many cases, visual testing may locate portions of a specimen that should be inspected further by other NDE techniques. Visual inspection is the process of examination and evaluation of systems and components by use of human sensory systems aided only by mechanical enhancements to sensory input such as magnifiers, dental picks, stethoscopes, and the like. The inspection process may be done using such behaviors as looking, listening, feeling, smelling, shaking, and twisting. Surface of the test specimen should be cleaned before inspection, where test specimen is illuminated and inspected using naked eye or with the help of optical aids such as mirrors, magnifying glasses, microscopes or video cameras. Visual testing requirements. 1. The inspector's vision. 2. The amount of light falling on the specimen, which is measured using a light meter. 3. The capability to process the visual data. 4. The level of training and attention to detail. The human eye is one of mankind's most fascinating tools. It has greater precision and accuracy than many of the most sophisticated cameras. It has unique focusing capabilities and has the ability to work in conjunction with the human brain so that it can be trained to find specific details or characteristics in a part or test piece. It has the ability to differentiate and distinguish between colors and hues as well. The human eye is capable of assessing many visual characteristics and identifying various types of discontinuities. Inspection requirements for visual inspection typically pertain to the vision of the inspector, the amount of light falling on the specimen, which can be measured with a light meter, and whether the area being inspected is in any way obstructed from view. In many cases, each of these requirements is detailed in a regulatory code or other inspection criteria. Mechanical and/or optical aids may be necessary to perform visual testing. Because visual inspection is so, the following list includes most optical aids currently in use. Mirrors, especially small, angled mirrors. Magnifying glasses, eye loops, multi-lens magnifiers, measuring magnifiers. Microscopes, optical and electron. Optical flats, for surface flatness measurement. Borescopes and fiber optic borescopes. Optical comparators. Photographic records. Closed circuit television, CCTV, systems, alone and coupled to borescopes/microscopes. Machine vision systems. Positioning and transport systems, often used with CCTV systems. Mechanical aids include measuring rules and tapes, calipers and micrometers, squares and angle measuring devices, thread, pitch, and thickness gauges, level gauges, and plumb lines. Welding fabrication uses fillet gauges to determine the width of the weld fillet, undercut gauges, angle gauges, skew fillet weld gauges, pit gauges, contour gauges, and a host of other specialty items to ensure product quality. At times, direct observation is impossible and remote viewing is necessary, which requires the use of optical aids. Optical aids for visual testing range from simple mirrors or magnifying glasses to sophisticated devices, such as closed-circuit television and coupled fiber optic scopes. Instruments for visual inspection. Videoscope. Advanced videoscope. Borescope. Microscope. Magnifying glass. Before any mechanical or optical aids are used, the specimen should be well illuminated and have a clean surface. After the eyeball examination, mechanical aids help to improve the precision of an inspector's vision. As specifications and tolerances become closer, calipers and micrometers become necessary. The variety of gauges available help to determine thread sizes, gap thicknesses, angles between parts, hole depths, and weld features. As it becomes necessary to see smaller and smaller discontinuities, the human eyes require optical aids that enable inspectors to see these tiny discontinuities. It is the interpretation of impressions transmitted from retina of the eye to the brain in terms of information about the specimen which viewed in the visual inspection. It depends on the vision acuity. Human eye has an excellent visual perception. Steps. 1. Recognizing the presence of defect in the specimen. 2. Identifying it. 3. Locating the defect of the specimen. 4. Noting its relation to the surface. 5. Identifying its features like size, shape, color, etc. Visual inspection classified into two types. 1. Unaided visual inspection / direct visual inspection. 2. Aided visual inspection / indirect visual inspection. Direct visual inspection. In the case of direct visual inspection, the component to be inspected is tested by an inspector. Testing, analysis, and assessment are carried out by one person. The direct visual inspection can be carried out with tools such as borescopes. Some simple tools used for direct visual examination include welding gauges, as seen here being used to check the fillet leg length. These tools, along with the most important tool for visual testing, our eyes, are quality instruments that can determine alignment, dimensions, and indications in all sorts of manufacturing products. Viewing angle range. Not closer than 150 millimeters. Angle must be 30 degree. Unaided visual testing. There is no interruption between the eye and the object. Aided visual testing. Magnification done by a mirror, a lens, an endoscope. Direct visual testing. Magnifying mirror. Telescope. Microscope. Direct visual testing. 1. Unaided visual inspection / direct visual inspection. It can be accomplished with the help of naked eye. Inspection can be done without using optical aids. Defects detected. Presence of cracks, corrosion layer, position of the cracks. Unfilled craters add contour of the welded parts. Surface porosity and general condition of the component. 2. Aided visual inspection / indirect visual inspection. Inspection can be performed using optical aids. Used to magnify the defects which cannot be detected by human eye. It permits visibility to areas which are not accessible to human eye.
Hello, I'm Dan Klingman with the Link Electric Weld School, and we just got done making several different welds, some lap joints, some T-joints, and some fillet welds, and also some groove welds. Now we finished those welds, but how do we now determine where do we need improvement at, and how do we determine whether those welds are acceptable? There's a couple general criteria that we can use to look at the welds and determine where we need to improve at. There's a lot of different types of what we call non-destructive testing, where you can still test the part, but it can then still be put into service. One of the most common types of non-destructive testing is the visual inspection. So when we look at visual inspection, we're going to take a particular joint, and we'll use this T-joint here to start with, and we're going to look at it, and there's a couple different parts of the weld that we should be familiar with. On this particular weld, we've got a toe of our weld here and a toe of our weld here. The part across the middle is what we refer to as the face of the weld. So when we look at this particular one and we want a flat face, you want that area from here to here to be relatively flat. The alternative would be to have a concave weld. Concave welds can be more susceptible to cracking than, say, a flat or even a convex weld, which would be slightly humped up in the middle. So we're looking for a flat face as the key. The other criteria that we're going to look at is proper placement in the joint. You know, obviously we want the weld to be in the joint. We don't want to be straying out of the joint. And I've got an example here of a lap joint, and we've got a fillet weld on here. And if you look right at the beginning, it's actually more on the bottom plate than the top plate. That's what we're referring to as proper placement. So you can see as we started the weld, we noticed we were on the bottom and then came back into the joint and proceeded down the weld. So again, making sure the weld is where you want it and it's properly placed is also a key criteria to look for in your welds. The other one is what we call, you're looking for the weld to be fairly uniform. And by fairly uniform, we mean nice and straight, and also, you don't have places where it's wide and narrow, wide and narrow. So for example, we built the pad earlier, or when you build a pad, the idea behind that is to get consistent with, number one, keeping a straight line, and number two, making sure that they're consistent in width as you proceed down the pad. So a fairly uniform weld is also an important criteria to look for when welding. And one of the last ones that we look at is the wash-in, and we'll select this one here. This is a lap joint, but when we refer to wash-in, if we go back and we look at the toes of the weld that we talked about, we want the transition at the toe of the welds to blend in smoothly with the base material. What happens is if it doesn't transition smoothly or have good wash-in, you could possibly get a stress riser there. And one of the examples that we commonly use for a stress riser to simulate this would be if you take a piece of string and you pull on it and it's hard to break. Well, if you go and you put a knot into it, like for fishing line or something, and you then pull on it, you'll notice that fishing line a lot of times will break right there where that stress riser was. Same thing in our weld here. We want it to transition smooth and have a nice wash-in with our base material in these particular areas at the toes. So as a summary, just to wrap up here what we've talked about, there's 4 general areas that we can focus on for visually inspecting a weld. One of them would be a flat face. One of them would be proper placement in the joint. One is fairly uniform, being the weld consistently shaped down the joint. And the last one is good wash-in at the toes of the weld. So if you're looking for any other information on welding, you can visit lincolnelectric.com.
Magnifying mirrors. It is also known as concave spherical mirrors. It is used to magnify the areas which are not accessible to human eye. Magnifying glass. It is also called as hand lens. This lens is used to produce a magnified image. Magnification depends upon the position where it is being placed between the human eye and the object. For higher power magnification, double or multiple lenses are used. Microscope. A laboratory instrument used to examine objects that are too small to be seen by the naked eye. Microscopy is the science of investigating small objects and structures using a microscope. Microscopic means being invisible to the eye unless aided by a microscope. There are many types of microscopes, and they may be grouped in different ways. One way is to describe the method an instrument uses to interact with a sample and produce images, either by sending a beam of light or electrons through a sample in its optical path, by detecting photon emissions from a sample, or by scanning across and a short distance from the surface of a sample using a probe. Microscope is used to magnify the image of a small object. Remote visual testing. The nature of the image is modified. For example, the optical image is converted into an electronic image by a camera. Remote inspection can be performed in locations that would be hazardous to human operators, such as inns, furnaces or high radiation areas of nuclear power stations, where thorough use is made of visual testing during plant shutdowns to test many critical components under high stress, such as nozzle junctions with the vessel cladding on nozzles. 1. Borescopes. Due to its rigid structure, endoscopes are limited to straight line access. 2. Fiberscopes. The introduction of glass fiber bundles and fiber optic image transmission enabled the development of the fiberscope. 3. Videoscope. Portable video inspection with zoom allows inspection of large tanks and vessels. Endoscopes are classified into 2 types. 1. Borescope. 2. Fiberscope. Borescope. which is used to inspect the inside of a narrow tube. It is a flexible tube with an eyepiece at one end and objective lens at another end. Light is passed through the lens and to obtain a clear image. Available range is 2.5 mm to 19 mm. Borescopes allow the observation in accessible spaces by a set of lenses in a straight, rigid housing. Using them, you can conduct testing in areas filled with water or oil. In place of the eyepiece, camera can be connected. Typical borescopes have diameter probes from 1.4 mm to 127 mm and lengths from 0.7 m to 2.7 m and up to about 90 meters, for specialized research pipeline. Field of view range 10 to 90 degree. Fibroscopes are flexible instruments that use a coherent fiber bundle to transmit an image back to the inspector's eye. A separate non-coherent fiber bundle is used for transferring the illumination from the light source to the inspection area. Dia range of about 3 to 12.5 mm and length varies between 6300 and 65 cm. Video borescopes can be used for many applications requiring remote visual testing, including the aerospace and power generation industries, engine manufacturing, and marine inspections. Video borescope systems can be used to confirm questionable results of other NDT techniques. For example, an indication can be located with ultrasonic inspection and then visualized with the video borescope. Another important area of visual inspection is in the aerospace industry, where remote visual inspection is performed on otherwise inaccessible areas of the fuselage, where in-service problems such as fatigue, cracks, or corrosion can occur on aircraft integrity critical components, such as pins joining the fuselage to the wings. Critical visual inspection of hollow helicopter blades is carried out using video borescopes, as well as the inner surfaces of jet engines and wings. The chemical industry makes wide use of visual inspection to test furnaces, combustion chambers, heat exchangers, pressure vessels, and numerous other areas within the plant. In the automotive industry, the internal condition of engines can be assessed, such as carbon deposits on valves, broken transmission gear teeth and gear wear being very easy to find. Factors affecting visual inspection / material attributes. Environmental factors. Atmosphere. Cleanliness. Humidity and temperature. Safety. Physiological factors. Physical comport. Health. Mental attitude. Fatigue. Factors affecting visual inspection / material attributes. Surface conditions. Cleanliness. Color. Texture. Physical conditions. Specimen conditions. Shape. Size. And temperature. Types of defects. Inherent defect. Formed during the initial production of raw material. X. Porosity, cavity, voids, etc. Processing defect. Formed during the processing of component. X. Surface and subsurface cracks developing due to mechanical and thermal processing like grinding, heat treatment, etc. Service defects. Formed during operating cycle of component. X. Surface and subsurface cracks due to fatigue, stress, corrosion. Defects identified by visual inspection testing are surface deposits, scaling, corrosion, discoloration, Oxidation. Advantages of visual inspection. It can be a very simple but effective test to perform and often does not need expensive equipment. Experienced operators and advanced equipment make it possible for visual inspection to be very sensitive. It allows discontinuities to be seen and not be just a blip on the screen. Many different surface breaking discontinuities can be found. Training and experience times can be short. Virtually any component can be examined anywhere on the surface. Disadvantages of visual inspection. Many variables can lead to discontinuities being missed. At its worst, it relies totally on the human factor. Many organizations pay little attention to the proper training of operators. Subsurface discontinuities will not be seen. References. Performance requirements for NDT are referenced in ASME Boiler and Pressure Vessel Code, Section V Non-Destructive Examination. Direct and remote visual testing is described in Article 9 of Section V Visual Examination.